In the first question, we are given a line and a transversal. And from that, we have constructed a quadrilateral. Now, this quadrilateral isn't just any regular quadrilateral. It is a parallelogram that was constructed here. And we know this because this construction is one from all the way back. It is a parallel line construction created by making congruent corresponding angles. Notice how these two angles here are in the same position, and one angle is copied to make the other. So these are congruent corresponding angles that form these parallel lines. And if you take a look here, these are also congruent corresponding angles created by copying the angle from one place to another. And since we have congruent corresponding angles, these lines are also parallel. So the opposite sides are parallel, formed by making congruent corresponding angles in the construction. Now, in the next question over here, what we're given is 3 points of a quadrilateral, and we're asked to construct with our compass point D so that ABCD would be a parallelogram. Now, the thing is, we can use the parallel line construction here, and we can copy an angle twice to create two sets of parallel lines. But that's a lot of work, and you might not exactly remember the parallel line construction, especially in June when you get to the Regents exam. So let's think about some other ways that we can construct a parallelogram. Not only are the opposite sides of a parallelogram parallel, but they're also congruent. So if we can make a quadrilateral that has both pairs of opposite sides congruent to each other, we'll know that it's a parallelogram. We're already given points A, B, and C. So I'm just going to connect them together so you can see what we're working with here. So already we have two sides of this quadrilateral that's ultimately going to be a parallelogram. I know that opposite sides are congruent in a parallelogram. So what I'm going to do first is I'm going to copy this side, and I'm going to replicate the same length over here for this side so that I can have equal opposite sides and find that missing point. So I'm going to put my compass on one endpoint of the line segment that I'm copying, and I'm going to just open up as best as I can to the other endpoint. And I'm just going to put a little arc to show that I measured. We try to be as precise as possible, but it's hard to get 100% accuracy. Now, without changing the distance on my compass, or if you're using the flat compass without changing the hole that you're using, I'm going to go over here to where one endpoint of the opposite side is, and I'm going to make that same arc. And then using my straight edge, I'm going to just connect from the point that I have to the arc that we just made. And that's where point D should be, because we copied this side and we made the opposite side the same length. We should also make sure that the other pair of opposite sides is congruent too, even though we can see where point D is going to be already. So what I'm going to do is I'm just going to measure this side over here, and then I'm just going to make sure that we have the same length here. And where those intersect, will be point D. And here I have a parallelogram, and I know it's a parallelogram because both pairs of opposite sides are congruent. Next, we're going to do another construction that we saw all the way back when in Unit 1, and we're going to construct a perpendicular line to the given line, AB, through point P. Now, if we want our perpendicular line to pass through point P specifically, then we have to start off with our compass point on point P. And what we're going to do is we're going to just, oops, let me make that smaller. That's real messy. We're going to just swing an arc. It doesn't matter the length or the hole that you use. It just needs to intersect the line segment in two spots. So notice that I have 1, 2 points of intersection. I'm going to take my compass and I'm going to go over to one of these intersection points. And you can use any distance. I'm just going to open up a little bit more so that it doesn't look too messy. And I'm going to swing an arc. And using the same measurement, I'm going to go over to the other intersection point without changing either my distance or the hole that I'm using. And I'm going to swing the same arc. And right through where those two arcs meet is where I'm going to use my straight edge. Oops, I did that really, really badly. It's hard to connect things together on the computer. Yeah, that did not go through either. I will get this. Okay, I just made a shorter line because it's hard to make this on the computer. And as you can see, when I use my straight edge and connect to the intersection point, it does pass right through point P. And notice how the line that we constructed is perpendicular to the original line. It does intersect it to form 90-degree angles. And it says over here, for which types of quadrilaterals would this construction be helpful? Well, it would be helpful if you're constructing a rectangle, since rectangles have 4 90-degree angles. And it could also be used for a square because squares also have 4 90-degree angles because they have rectangle properties. And we also know that a rhombus has perpendicular diagonals. So maybe in some way, this could be used for some sort of rhombus construction as well. Okay. Here we are given a rectangle, and we're going to construct the midpoints of all 4 sides of this rectangle. We construct the midpoint by making a perpendicular bisector. So I'm going to do this side, this top side first. I'm going to just put my compass on one of the endpoints, match up as best as I can. And I'm going to open up about 3/4 of the way down. The exact distance doesn't matter. More than halfway, about 3/4 down. Oh, let me zoom out here so you can actually see. That's what's annoying about the computer as well. And then using the same distance, I'm going to come over here and I'm going to make the same arc. And you can't see where they intersect on the top, but there should be a top intersection as well. And right through those 2 intersection points, I'm going to make my perpendicular bisector. And this cuts the side of the line segment in half. So that would be the midpoint of this side. And at the same time, it also gave me the midpoint of this side. So now I just need to find the midpoints of these 2 sides that are remaining. And we're going to do that using the same construction. If I can grab my compass, there we go. So I'm going to go over, once again, to an endpoint of the side that I'm bisecting, about 3/4 of the way down, make an arc, and then on the other endpoint, make the same arc. Here I have my perpendicular bisector. So here is my midpoint of the side. And then finally, one more side to go. I connected that one really badly. Let me try that one more time. Okay. And now that I have the midpoints of all four sides of this rectangle, what I'm going to do is I'm just going to connect them together to form a quadrilateral. And the question is, what kind of quadrilateral is this? And you might be thinking that this is a rhombus because it looks like one. And in fact, it is a rhombus. And let's talk about why. The outer quadrilateral that we started with is a rectangle. So that means the corner angles are all 90-degree angles because that's a rectangle property. We also found the midpoints of all the sides. And we know in a rectangle, the opposite sides are congruent to each other. So this side and this side are congruent. And since they're both being split in half, the pieces of the sides, the halves of the sides, are all congruent. For example, if these were both 10 and now we have them, then they would both be 5. Same thing with the other pair of opposite sides. They're congruent. And since we constructed the midpoint, the halves are congruent to each other. So now we can say that all four of these right triangles surrounding the rhombus, surrounding the quadrilateral, I should say, are congruent to each other by side angle side. And since we know these four triangles are congruent, then we can say the corresponding sides of those triangles are also congruent due to CPCTC, because we already know the triangles are congruent. And now we know that the inner quadrilateral is a parallelogram because both pairs of opposite sides are congruent. In fact, all the sides are congruent. So not only is it a parallelogram, but it is also a rhombus. The last part of the question says to find the area. So we're told that the length is 8. And since we constructed the midpoint, that means each half is 4. And we're told that the width is 6. And since we constructed the midpoints, that means each half is 3. We have 2 sides of each of the right triangles, and we can find the hypotenuse using the Pythagorean theorem. And these are actually Pythagorean triples. So they are 3, 4, 5 triangles. So I already know that these are all 5. One way that you can find the area of a rhombus is base times height. And although we have the base, we don't really know what the height is of the rhombus. A second way that you can figure out the area of a rhombus is you can multiply the 2 diagonals together and you can divide by 2. So let's do that way. Let me just wait for my line tool over here to work. So from here to here, this diagonal is the same length as the side of the rectangle, which is 8. And from here to here, oops, from this computer is annoying. And from here to here, this diagonal is the same length as the side of the rectangle, which is 6. So that would be 8 times 6, which is 48, divided by 2, which is 24. So the area of this rhombus is actually 24. Moving on to the last question here. What we're going to do is we're going to construct an equilateral triangle with its vertex at point R, and the length of a side of this equilateral triangle is going to be the length of a diagonal of the rectangle. And it doesn't matter which diagonal you use because diagonals of a rectangle are congruent. So I'll just pick that one. I'm going to take my compass and I'm going to measure the length of the diagonal. I'm going to measure from one endpoint to the other. And it's a little bit too big for my compass here. That's another thing that is annoying about using the computer compass. So I'm going to have to do this in two pieces. So I'm going to take my measurement without changing anything, and I'm going to bring it down over here. And then since my compass doesn't extend that far, you can do it in one shot, just measure the diagonal. I got to grab the other piece. And now I have the next vertex of the triangle. And I'm just going to use the same distance from R to this point, the length of the diagonal, to make the two other sides. Unfortunately, my compass only extends so far. Oh, I think it got there now. Yes, it got there this time. So with my compass point still on point R, I'm going to just extend my compass upwards and swing an arc. And then I'm going to go over to the vertex that we found of the triangle using the length that we measured. And I'm going to make the same arc. All of these arcs were with the measurement of the diagonal. And now we're just going to connect to the intersection points. And here we have an equilateral triangle where all the side lengths are the length of the diagonal of the rectangle. Next, it says to construct the midpoints of two sides of the triangle. So let's do it. To construct the midpoint, we're going to do a perpendicular bisector like we did in one of the previous examples. So I'm just going to put my compass on one of the endpoints, about 3/4 down, arc above and below, other endpoint, and same arc. Then we're going to repeat and do the same thing on another side. I'm going to use this side over here on the right. And then it does say to connect the midpoints of the sides together. And then it says to find as many angle measurements as we can. We started off with an equilateral triangle. So all three of the angles measure 60 degrees as they do in any equilateral triangle. And since we started with an equilateral triangle where all the sides were the same length, and then we cut them in half, since this side and this side were the same, and we halved them, each half should be the same. So we know that in this top triangle, these two angles should be the same if it has two congruent sides. So that means each of these angles have to be 60 as well, making the top small triangle also equilateral. Notice we have congruent corresponding angles, and that proves that we have parallel lines. So what we have here at the bottom, this quadrilateral, is a trapezoid because it has one pair of parallel sides. We're going to take a look at one more question. It's the last one over here. We have parallelogram ABCD adjacent to rhombus DEFG, and we're told that angle B is 118 degrees and angle AHC is 138 degrees. Since ABCD is a parallelogram, opposite angles are congruent. So if angle B is 118, its opposite angle D will also be 118 degrees. We also know that consecutive angles in a parallelogram are supplementary. So if I do 180 minus 118, I get 62 degrees. So this angle would be 62 degrees, as will this whole angle be. And these are supplementary. So that means this angle here will also be 62 degrees because these form a linear pair. We should keep our goal in mind. We want to find this angle over here. And we do know that DEFG is a rhombus. Let's see what other conclusions we can draw. I knew that this was 138 degrees, and it's vertical to this angle. So this should also be 138 degrees as well. And together, these two angles form a linear pair. So let me do 180 degrees minus 138, and I got 42. And that means this angle here is also 42 degrees because they are vertical angles as well. Rhombuses have the same parallelogram property that opposite angles are congruent and that consecutive angles are supplementary. So if this angle of the rhombus is 62 degrees, then so is this whole angle of the rhombus opposite from it. Also, since consecutive angles are supplementary in a rhombus, we have 118. And for angle FGD, that should also be 118. So now we have two angles of this triangle, and we can find the third one. I'm going to do 118 plus 42, and that's 160. Subtract that from 180 degrees, and I got 20 degrees for the angle that we're looking for here.